Welcome to the first video in the Class 16 series of lecture videos. This class is going to be a little long, but we'll hopefully get through it understanding our SN1 and SN2 mechanisms and our E1 and E2 mechanisms a little bit better than before we started this class. So let's talk about elimination. So say we have 2-bromo-2-methyl-propane and we put it in ethanol. And so yes, we expect to get an SN1 substitution product where the bromine popped off of our molecule. We eventually got some HBr, and our ethanol, the ethoxy ethyl part of it, substituted into our carbocation. And so yes, we get 80% of this SN1 product. However, we also get a small amount, 20%, of something called an elimination unimolecular product. And so that's E1. And what is it? It's an alkene. Well, how many carbons are in this alkene? 1, 2, 3, 4 carbons. How many carbons were in our 2-bromo-2-methyl-propane? 1, 2, 3, 4. So let's investigate how this product arises. So like I said, E1 is unimolecular elimination, and it's going on at the same time that SN1 is going on. It's very difficult to avoid. It shares the same intermediate, and so the rate determining step for SN1 is also the rate determining step for E1. Our bromine leaves as bromide and we form a carbocation. And so we know that our tertiary carbocation that we formed is stabilized by a property called hyperconjugation. And that is where we have donation of electron density from this adjacent carbon-hydrogen molecular orbital into the empty p orbital on this carbocation. Well, instead of our ethanol taking a lone pair and making it all the way into our carbocation to form a bond and eventually get deprotonated to give us the SN1 product, it might bump into the proton on the carbon adjacent to that carbocation and pluck that off. And then the electrons in that carbon-hydrogen bond go to form a double bond. And that's how our E1 product arises. Of course, we get protonated ethanol and bromide, which is simply HBr in ethyl alcohol. So the hydrogen atom on the carbon adjacent to the carbocation must be acidic because ethanol is a fairly weak base. So what's going on? Here we've got a representation of our carbocation. Here we have the sigma star carbon-hydrogen bond. We can see, oh, we've got some lobes on carbon that sort of almost look like they're of appropriate shading and ability to overlap with our carbocation's empty p orbital. Our ethanol comes along, we donate some electron density into this sigma star carbon-hydrogen molecular orbital. We snag the hydrogen, so we're protonating ethanol here and putting electron density in that orbital, and lo and behold, once we've left the electrons behind on carbon, we go to form a pi bond, right? Because we have now two p orbitals. They're of the same phase on the same side of the plane of the molecule. This carbon over here had a formal positive charge. This carbon now has 2 electrons. Why don't we go ahead and form our pi bond, which has 2 electrons? And there's our pi molecular orbital. So hopefully this cartoon is illustrative of what is going on in this reaction. So a little bit more on this before we can end our video. Here we've got what? 2-chloro, 2,3-dimethylbutane, and we throw it in water. Here we've got our major product where we substituted the chlorine for a hydroxyl group which came from water. That's our major product. We would expect small percentages of E1 elimination products. We'll talk a little bit more about which one of these might be favored under what conditions when we get to our chapter on alkenes. So it's very difficult to avoid elimination. How can we favor E1 versus SN1? Well, let's look at a case where the SN1 is favored first. Here we've got tert-butyl alcohol. We're adding concentrated HBr, and Le Chatelier is driving to the right. We get our 2-bromo-2-methylpropane and water. If we added this to an ocean of water, Le Chatelier would drive to the left. What's the mechanism going from left to right? Well, our hydroxyl group gets protonated by the HBr. We form something that looks like water. It comes out as a leaving group. Our bromide is hanging out, counterbalancing that positive charge, formal positive charge, until the water comes out. Now the bromide formal negative charge is counterbalancing the carbocation, but it feeds right in, creates a bond, and we have made our 2-bromo-2-methylpropane. So how do we favor the E1 product? So we have E1 going on. It's a byproduct. It's not the major product for this particular reaction. Well, that's a good question, right? To favor E1, the conjugate base of the acid should be non-nucleophilic. Also, we could remove one or both products of the E1 reaction as they are formed. So that's another principle for Le Chatelier, right? We drive this reaction to the right by removing one or more of the products as they are formed, so they don't have the opportunity to go backwards. So here we've got our tert-butyl alcohol, and instead of HBr, whose conjugate base bromide is a fairly good nucleophile, we use H2SO4, sulfuric acid. So the hydrogen sulfate is not a strong nucleophile. What's the mechanism? Our alcohol gets protonated by our H2SO4, we form water, we've got HSO4 minus as a counterbalancing anion. Our water leaves. Now this HSO4 minus is not a good nucleophile. And in fact, water is more basic than the HSO4. So water will snag a proton, and we create an alkene, and of course we have H3O plus and HSO4 minus, which is what would happen to sulfuric acid in water. It would simply dissociate because sulfuric acid's a strong acid. Why is HSO4 minus not a really strong nucleophile? Well, that negative formal charge on this oxygen is not located simply on this oxygen. You can write a number of resonance forms where that negative formal charge on oxygen is delocalized onto the other oxygens. So that pretty much finishes this lecture video, and I'll see you in the next one.